Nothing beats. We're going to now look at what is called higher order derivatives. Continuing with our derivative discussion, let's take a look. So, statement right here, just noting that, well, we can find a derivative of a function, assuming it's differentiable, of course. And just like we can take a derivative of a function, we can also take derivatives of derivative functions, because a derivative function is itself a function. So how does this all work? We're going to look at the notation, different types, and then we'll try to find a few. All right, first of all, for instance, let's say we differentiate the function f prime of x with respect to x. Now remember, f prime of x is the derivative of some function f of x, and it's a function itself. So if I differentiate f prime of x with respect to x, I get a new function, the second derivative of the function f of x with respect to x, and we call that f double prime of x, if you will, hence the two dash marks right there indicating I have differentiated the function f twice. But we don't have to stop there. What if we went ahead and took the derivative of the second derivative with respect to x? The third derivative of f of x is the result of doing this. And we could refer to that as f triple prime of x. So you can imagine we just keep doing this, assuming all these derivatives exist, of course. Just keep differentiating derivatives, differentiate second derivative, go ahead and differentiate the third derivative. Just keep going, right? And in general, if we have a function, f of x, and we assume it's n times differentiable, meaning that I can take the derivative of it n times, and that function will exist, then we say that the nth derivative, maybe it's the 20th derivative, maybe it's the 50th derivative, whatever. That nth derivative is defined just like so. If I take the derivative with respect to x of, say, the n minus 1th derivative of the function, I get the nth derivative of the function. So you notice some notation here, specifically right there. Right now, just a moment ago, we saw the second derivative was f double prime of x. Third derivative, f triple prime. And you can imagine just keep making these primes, right? But at some point, it's going to be too hard to deal with. If you have to write 50 dash marks, f prime, 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 and so on, it's not a very efficient way of denoting something. So when we say the nth derivative of a function, we write that superscript there, but in parentheses, okay? Right there. That parentheses indicates I have taken the derivative of the function n times. And not to confuse that with when we raise a function to a power, remember, when I take a function and I raise it to some power, say n, well, I could write that as fn of x, like so. So that's not the same thing as this, right? That parenthesis right there in the superscript is really indicating a derivative, not a power. Okay, of course, and this up here is valid for n not equal to -1 as well, since that's an inverse function. So don't confuse the two notations. Here's our new notation, though, for derivatives. Higher order derivatives, the nth derivative, like so. Now, we also have equivalent Leibniz notation for higher order derivatives. So higher order, by the way, just means higher than the first derivative. Now, again, let's assume we have a function that's n times differentiable. Okay, so I can just keep differentiating as much as I want. Then we can write the second derivative here, f double prime of x. Think of that as differentiating the function y is f of x with respect to x, and then I take the derivative with respect to x of that. So it means exactly the same thing as f double prime, but the notation here, which we want to note right there, you see the 2 is now kind of almost like an exponent. It's not an exponent, though. appearing on the d in the numerator and the x in the denominator here in this notation. And what that's saying is I have differentiated the function y is equal to f of x with respect to x twice. And that's also consistent with the notation right there. So we can pronounce that, if you will, the second derivative of y with respect to x. So you might kind of guess what the f triple prime of x would look like right here. F triple prime of x is the same thing as, okay, I differentiate my function y with respect to x once, then I'm going to differentiate that, then I'm going to differentiate all of that. So I'm differentiating y with respect to x 3 times. And of course, that's the same thing as differentiating the second derivative of y with respect to x with respect to x. And you see the notation here, d cubed y over dx cubed, if you will, or the third derivative of y with respect to x. So those 3's just indicate notation that I've differentiated the function y 3 times with respect to x. And you can imagine keep doing this and so on and so on. And so in general, the nth derivative here of an n times differentiable function y is equal to f of x is this notation right here. So we already saw this notation a moment ago. That's the nth derivative of the function f with respect to x, or equivalently, we can write it in Leibniz notation like so. So put that little n on the d as a superscript and the n on the x as a superscript, and that is telling us we have differentiated the function y as f of x n times with respect to x. So we should know both notations because they appear in various situations. And now that we've kind of introduced that notation, let's go ahead and just find a couple of derivatives that are of higher order. So in this example right here, we're asked to find the third derivative of y with respect to x, where y is this function g of x, which is 4x cubed minus 5 times e to the x. Coffee sip. Hold on one second. Okay. So let's do this. I have to differentiate that function 3 times. Now, of course, in this situation, the third derivative of y with respect to x is really just the same as saying g triple prime of x here, or if you prefer, the third derivative of g with respect to x. All those mean the same notation. So let's do it. I have to differentiate this 3 times. So first things first, what is the first derivative of this function g of x with respect to x? Well, let's differentiate it. Differentiate with respect to x what function? Well, 4x cubed minus 5 e to the x. And from the previous couple of videos, we now know that how to do that, right? It's power rule for the 4x cubed. And then the derivative of e to the x, of course, is e to the x, with the constant multiples sticking around and the sum and difference rules also applying. So bring down the 3 on the x cubed, it gets multiplied by the 4, and you get 12x squared. And then the derivative of e to the x, again, is e to the x. So the derivative of 5e to the x is just 5e to the x. So 12x squared minus 5e to the x. So there's my first derivative, right? But I'm not done. I gotta find a third derivative, so I better differentiate again. What is the derivative with respect to x of the derivative of y with respect to x? Remember, this is the same as writing d squared y over dx squared, the second derivative of y with respect to x. And that's just the same thing as differentiating the function with respect to x, the derivative that we just found, right? So differentiate 12x squared minus 5e to the x to obtain our second derivative. And applying the power rule again, and also the derivative of e to the x, we are going to get 24x minus 5e to the x. So there's my second derivative. And then finally, we need to find a third derivative. So the third derivative here that we're after, d cubed y dx cubed, let's write that out, d cubed y dx cubed, the third derivative of y with respect to x. That's the same thing as differentiating the second derivative of y with respect to x with respect to x. So that's just the derivative with respect to x of the function we just found, 24x minus 5e to the x. And then finally we obtain our third derivative here, 24 minus 5e to the x. And there's my third derivative of the function g of x as given in this problem. So there's one example. Basically just differentiate the number of times it tells you to do. Let's look at one last example before we end the video here. In this example, we have the function k of t, which is this polynomial function negative 6t to the fourth plus 5t cubed minus 4t squared plus 5t minus 8. We are now asked to find the fourth derivative of this function with respect to t. So let's do it. We got to differentiate that function 4 times. First derivative, k prime of t. Well, I'm differentiating that entire function, right? So the derivative with respect to t of negative 6t to the fourth plus a 5t cubed minus a 4t squared plus a 5t minus an 8. So I differentiate that, keeping in mind our power rules and our constant multiplier rules and our derivatives of sums and differences. So term by term, we get a negative 24t cubed plus a 15t squared minus an 8t plus a 5. There's my first derivative here, k prime of t. So therefore, k double prime of t, the second derivative, well, that's going to be the derivative of the derivative that we just found. So differentiate with respect to t, a negative 24t cubed plus a 15t squared minus an 8t plus a 5. What do we get? Power rule, negative 24 times a 3 times t squared, and then plus a 30t minus an 8. Remember, derivative of constant is 0. Now off on the side, what's 24 times 3? Do it old school because I ain't got my calculator next to me. What do we get? 2, 1, 6, 72. All right, so this is the same as negative 72t squared plus a 30t minus an 8. Nice. So there's my second derivative. Keep going here. 2 more to go. K triple prime of t, the third derivative. That's going to be the derivative of the second derivative that we just found. So differentiate with respect to t, the function negative 72t squared plus 30t minus an 8. What do we get? We get a negative 144t plus 30. Power rule. And finally, we're going to get the fourth derivative here. Fourth derivative of k with respect to t is going to be the derivative with respect to t of the third derivative, negative 144t plus a 30, and we end up with just negative 144. So the fourth derivative of this fourth degree polynomial in this case is just the constant, negative 144. And there you have it. So what we do in this video, we discussed how you can differentiate derivatives, finding higher order derivatives. We can find a first derivative, second derivative, third derivative, fourth derivative, all the way down to whatever derivative we want, nth derivative, assuming a function is n times differentiable. And then we went ahead and also explained the notation for those things and looked at a couple of examples here, finding some higher order derivatives. Now, conceptually, some of these higher order derivatives do have a more deeper meaning. And later in this discussion of calculus, we will get into depth about the meanings behind these derivatives, at least in relationships to their graphs. But that's it for this one. This is Math and Beats. Until next time, I'm out.